Hi everybody. Today we're going to recap what we started in class. So we're going to talk about circular motion. And if we're going to talk about circular motion, it's important to keep in mind that all of the physics that we already know, so everything dealing with kinematics and dynamics, is really important to us in developing an understanding of uniform circular motion. And, it's probably a good thing because we know a lot about kinematics and dynamics. So to get us started here, let's think about some object moving in a circle. And let's imagine that this object has a constant speed. So when you hear the term uniform circular motion, what that means is that an object moving in a circle at a constant speed. And if we imagine a case like this, my question for you today would be, is there any acceleration? Well, let's think about this. We know that acceleration is delta v over delta t. So if we have some object moving at constant speed in a circle, we know that it's changing position, and we can analyze different positions in this uniform circular motion. So for example, at this instant, the velocity can be represented by a vector. Here, I'll call this v1. And at this instant, the velocity can be represented by a velocity vector, which I'm going to make the same length as I made the first one. But we can see that the direction of that vector is different. And I can really choose any point in this path here and represent the instantaneous velocity at that position in time. So when we talk about uniform circular motion, we can have this constant speed, length of these velocities are the same, but the direction component of each velocity is different. So when we think about acceleration, it's a change in velocity over a change in time. And even though the magnitude of the velocities has not changed, the direction of each velocity has changed. So, yes. There is acceleration because there is a change in velocity. And that change comes in the form of this changing direction. So its velocity changes, therefore the object is accelerating. What I want to take a look at now is I want us to start to think about, and this is kind of some of the ideas that we developed today in class. I want to develop this quantitative concept of the acceleration of an object that's moving in a circle. So if we can, again, consider an object moving in a circle. And what we want to do is think about 2 points on the circle that are not too far away in terms of time. So if I want to think about, call this point 1 here. And at point 1 is the center of the circle. We can represent the radius here. So I'm just going to label this R. And I don't want to go too far away from my circle. So I have this labeled R. And right here I'm going to talk about the velocity at this point. And so the velocity vector, again, is going to be tangent to the circle. Okay, I'll call this V1. The next thing I want to do is I want to think about a second point on the circle, not too far away from my original point here. It's not really that clean. Sorry, I'm still getting used to this new tablet I got for Christmas. All right, sorry guys, let me see if I can model this a little bit cleaner for you. I'm going to have to delete this part. Okay, so I have a good circle here for you, finally. And what I'm really interested in doing is finding 2 points in this circle so that we can analyze how velocity changes in some type of quantitative way. Okay, and I think that we can use a familiar form in which to do that. We can look at the velocity vectors. So this r here is going to stand for the radius of the circle. And so from the center to here, all right. And what I really want to do is choose 2 points. Okay, and again, this radius here, this length, and this length would be the same number. Okay, the radius of the circle is going to be the same. And I really want to analyze the velocities at these 2 points. So we know that the velocity is going to be tangent to the circle. So at this point, we can represent that vector here, v1. And right over here, we can represent that vector here. And notice they're about the same length here because we have uniform circular motion. We're talking about an object that's going at a constant speed, but there is a velocity change because moving in a circle requires a change in direction. So what I want to look at next, we have this this problem set up. We want to take a look at this change in velocity. So what happens between v1 and v2 in this time interval? Well, one of the things that we know that is interesting is that this, okay, this right here represents the distance traveled in this time interval, right? So this little purple segment here represents the distance traveled. When I take a look at this velocity 1 vector and velocity 2 vector, I know that I'm actually able to find delta v if I want to. Delta v would be v final minus v initial. So in this case, that's v2 minus v1. Now, we're very used to adding vectors, right? I mean, we add force vectors all the time. If we wanted to add v2 plus v1, that would be a pretty easy task for us, right? I mean, we would take the head of this vector, right, and the tail of this vector, and we could line them up and we would add them. But in this case, what we're doing is we're trying to subtract vectors. And when we subtract vectors, what that really means in terms of these actual arrows here is taking v2 and adding it to the opposite, right, of v1. So again, taking v2, I'm just going to sketch my v2 down here. And really what I want to do is take this v1, right, and I'm looking to take the opposite direction, V1. And if I want to find delta V, my delta V is here. This is my delta V. And very interesting, this delta V is towards the center of the circle, which all the experiments that you did in class yesterday and today keep coming up with this pattern of delta V and acceleration vectors for objects moving at constant speed in a circle to be towards the center of the circle. And we do find this again here. What's interesting is that when you look at this radius distance traveled triangle, we know, for example, that two of the legs of this triangle, this R and this R here, are equal lengths. And we also know that if this object moves at a constant speed in a circle, that this V1 and this V2 are equal lengths. So what we're dealing with here are two isosceles triangles. Even more interesting is the idea that when we look at this angle here between the two radii, it's also the same angle as this change in velocity. So where these two velocities meet here is the same angle. So what we're dealing with is two similar isosceles triangles. So in the one triangle, speed is equal. This V1 and this V2 are equal. And in the second isosceles triangle, the radii are equal. And that's kind of neat, because what we can do is maybe we can use this to our advantage, and we can look at these values that are similar. So, for example, we know that distance, right, related to the radius is going to be similar to this delta V here, related to either of the speeds. So I'm going to use V for speed here. And I can, basically come up with an expression for delta V based off of this relationship, right? I know that delta V here is distance times speed all over the radius. And if I'm really looking to develop some quantitative relationship for acceleration, then what I'm really looking to do is dividing both sides by delta t. That can help me derive an equation for acceleration. So if I divide this side by delta t, and I can also divide this side by delta t, a couple of interesting things happen. First of all, delta V over delta t, there's the acceleration that we've been seeking here. And when I have distance divided by time, like I do right here, distance divided by time, that's our velocity. So now we have a V times V all over R. And so what we come up with is acceleration equals V squared over R. So once you complete the vector subtraction, like we did in class today, we know that this delta V vector and the acceleration vector, again, they keep pointing towards the center of the circle. And so this type of acceleration is special in physics. And so we call this a centripetal acceleration. Centripetal is this kind of fancy word that means center seeking. So this is centripetal acceleration. And what you'll see is this capital A with a little subscript C. And so you've derived it yourself in class today, and this is just a brief recap here of where it comes from.